Welcome to All Space Considered. It's the first Friday of May, everybody, and we've got a great show for you. As you can see here, we have our social media and our email address if you want to contact us, and we're always happy to have people reach out to us. And let's go through our show here. Well, hang on just a second. I'll get to the next slide here. There we go. I'm pushing the wrong buttons. Anyway, our show, of course, All Space Considered, comes from Griffith Observatory, which is owned and operated by the city of Los Angeles. And also, we'd like to thank Griffith Observatory Foundation, who's our nonprofit partner in so much of what we do. And we're from the Division of Recreation and Parks. So this is a service to all the people of LA and all the people out there watching tonight. And we've got a great show, like I was saying tonight. It is May 6, 2022. Right off the bat, we're going to start with Dr. Jessie Christensen. She's project scientist, NASA Exoplanet Archive research scientist, and NASA Exoplanet at the NASA Exoplanet Science Institute. Anyway, we're super excited to talk exoplanets, obviously, tonight with her. She's coming straight from a conference in Vegas, which is going to be great to hear about. We also have, of course, as we do every month, pretty pictures in solar system weather with Katie. And we'll have a sky report with Patrick. We'll talk a Mars update. We'll talk about what's been going on Mars. We'll give you an update about that largest comet that was discovered. And also the most distant galaxy. It's changed yet again. There's a different most distant galaxy now. And we've got Psyche and the Europa Clipper. And then we'll do Out to Launch. And then we'll talk briefly about the decadal survey, the Planetary Science Decadal Survey. Daniel will be bringing you that information, and we'll end up talking with some ice volcanoes on Pluto. So that's our show that we'll have for you tonight. First of all, I was talking about that exoplanet conference. The first one was called Exoplanets 1 in Davos, Switzerland. Then they had, cleverly, Exoplanets 2 in Cambridge, UK, and that was in 2018. Then 2019, they took a break. There simply wasn't one. And then 2020, Exoplanets 3, and that was done virtually on the internet. And now Exoplanets 4 came from Las Vegas, Nevada, my home state, and we're lucky to be hearing about anything that happened there in Las Vegas, of course. And like I said, we're happy to have Dr. Jessie Christensen with us tonight. And Jessie, hello.
Hi, everybody. It's a real pleasure to be here. Thank you for having me. So yes, let me tell you one story about Vegas, and I can tell you this story because it actually wasn't me. So I had heard for a long time, there was this legend of this physics meeting in Vegas, where the physicists had been asked to never come back again. And everybody thought this was apocryphal, like just a legend made up story. But just recently, I actually found the truth. So in 1986, the American Physics Society, the APS, had a meeting at the Grand M Resort in Vegas. Now, when casinos rent out their hotel rooms for people who are coming to a conference, they try to outbid each other because everybody wants this like group of thousands of people to come to their casino. So they offer the rooms really cheap, thinking they're going to make it back on the casino floor. So the Grand M did this. They put the rooms out really cheap for this big conference that came to town. It was the worst week they ever had, the worst week takings ever. And it's because physicists understand statistics, right? Scientists have a pretty good grasp on statistics. So like a roulette wheel, you don't have a good chance. So the physicists just didn't play. So the casino's whole ploy that they were going to make this money back on the casino floor did not pan out. So I won't tell any stories about this Vegas trip, but suffice to say, this is the first time physicists have been back to Vegas in a long time.
Wow, that's great.
Yeah, I wonder if a few of them were even counting cards. I know, or other means. Up at Santa Cruz, where I was a graduate student, they had in a glass case one of the shoes that they had implanted computers in, and they were actually tapping to the rate that the ball was going around on the roulette wheel, and they were able to bet quadrants and make money on that. They were calculating where the ball would fall on the roulette wheel. But I think they eventually did get caught on that one.
I see.
So we have exoplanets in store. I can't wait to hear what you're going to tell us about and the latest on the exoplanet front.
Yes. All right. So let me take it away then. I'm going to advance the slides and it's working fantastic. So we did have a lot of really good fun exoplanet news in Vegas this week. And I'll discuss one brand new result right towards the end of the talk because it's very cool. And I was really excited when I heard it earlier in the week. And it's relevant to one of the planets I'm going to talk about. But the talk today is called Truth is Stranger Than Science Fiction. So let's get into it. Okay. So if we were in person and, I had a really fantastic time the previous time I gave a talk at Griffith Observatory. So I hope I'm back there in person one day. If we were in person, I would ask for a show of hands who recognizes this planet. And then I would give you a bit of a clue. I would put the Enterprise in front of it. This is Vulcan. This is Spock's homeworld in Star Trek. It's also known as Vulcan, Vulcanus A2, Navasa 2, or 40 Eridani A2. Now, the thing is, people have been thinking about exoplanets for a really long time, a really, really long time. More than 2,500 years ago, the Greek philosophers were thinking about the idea of whether there were other Earths. Was Earth singular or plural? Were there many Earths? And Plato and Aristotle actually argued for the uniqueness of Earth. They said there's only one, there can be only one, the original Highlander, Earth. So more than 2,000 years ago, we're thinking about this idea. And at that point, it's purely hypothetical, right? Like these guys are still trying to work out what stars are, let alone the arrangement of a planetary system. But they're already thinking about whether there are other Earth-like planets out there. Now, in fiction, so that's in science. In fiction, we first start to see stories going off-world as early as Dante's Paradise in around the year 1300. So Dante kind of explores this story where different events in the plot happen in concentric spheres centered on the Earth, going outwards, Mercury, Venus, Mars, Jupiter, and Saturn. So he's like one of the first people that really starts taking fictional stories off-world, just to be like, where else can we set our very cool stories? In the science side, a few hundred years later, we're in 1592, we're in the Renaissance. So in the Western world, the Renaissance is an incredible time for literature and art and science and math in the Western world. And there's this Italian mathematician whose name is Giordano Bruno, and I'm going to read this quote. There are countless suns and countless Earths, all rotating around their suns in exactly the same way as the 7 planets of our system. And I'll leave it as an exercise to my very educated listeners. In 1592, which 7 planets was he talking about? So not only did Bruno come up with this thought that there are countless Earths out there, he also very succinctly identifies the problem, which is that stars are very big and very bright and very luminous, and planets are not. Planets are much, much smaller and much, much dimmer. So when we're looking at the stars in the sky, we're blinded by the light from the stars, and it's very, very hard to see the planets. Bruno was eventually murdered, burned at the stake for saying, amongst other things, this thing about multiple worlds, because he was in Rome at a time when it was not good to say things against the Roman Inquisition. So he was actually burned at the stake. Thankfully, these days, as a planet hunter, I don't have to worry about that so much. Okay, back to fiction. In the 1600s, we see a novel by Mary Cavendish called Blazing World. This is an amazing work of fiction. And, one of the very, very first things you see where in the book, this boat goes through a portal basically at the North Pole and arrives in a fantastic world, like a brand new world, clearly a fictional world, not one of the planets of our solar system, but she's creating a brand new world. And that's super exciting to see that start to emerge in our science fiction and our fantasy literature. Over the next few hundred years, the 1700s, 1800s, 1900s, you start to see heaps of people explore this idea in their fictional stories of setting stories on mythical planets, not planets we knew, brand new made up planets. Okay, in science, so we're up to the 1950s. So we've had this idea for a long time that planets might exist out there around other stars. And Otto Struve, who's an astronomer, he suggests this idea. So what they knew about at the time in the 1950s were stars, binary stars. So 2 stars orbiting each other very closely. And in fact, the majority of stars are in multi-star systems. Most stars are in multi-star systems. So they knew about binary stars. And one way they could see these binary stars was if you looked at the light from the star and split it out and looked at different wavelengths of the light, you could see that sometimes the light was coming towards you and sometimes it was going away. And then it would come towards and go away, come towards and go away. And that's happening because these two stars are orbiting each other. And sometimes the star is coming towards you and sometimes it's going away. So Otto Struve has this idea. He's like, hey, what if we took one of those stars out and put a giant planet there instead? Maybe that's a way we could detect these planets by their gravitational pull on the stars and the measure of the starlight. Now, they'd have to be very close to their star, like these binaries that they had seen with periods of just a few days. So they orbited each other very quickly, just every few days. But it was conceivable that you could measure the light from the star wobbling because of this giant planet. Now, interestingly, at that point, the only system we knew with planets was ours. And our system doesn't have a giant planet right next to the star, right? We've got the 4 rocky planets that are close in, and then we've got the 4 giant planets that are further out. So a bunch of people were like, Otto, that doesn't make any sense. Like, you can't have a giant planet next to the star. There's no way for it to form there. It will just get swallowed by the star. That doesn't make any sense. So for a long time, this paper was ignored. So for the next 50 years, this paper has 7 citations. All right. In fiction, we move to the screen. So in the 50s, things start to happen in film. We have our first exoplanets, our first fictional planets appear on film. When Worlds Collide in 1951 and Forbidden Planet in 1956 are some of the earliest examples of films with exoplanets in them. And on TV, 1963, one of my favorite franchises of all time, Doctor Who, we finally see on TV on the small screen, they start exploring fictional exoplanets. That's very, very cool. All right, so 40 years after Otto Struve comes up with this idea that you could measure a starlight wobbling because of the gravitational pull of a planet, the very first planet is found orbiting a star like the sun with this method. And just a few years ago in 2019, the 2 Swiss astronomers who discovered that planet won the Nobel Prize in physics for this really incredible discovery. So in the first 40 or 50 years of Otto Struve's paper existing, it had 7 citations. Since then, in the last 2 decades, it's had over 100, as everyone's like, oh, dang, he actually called it. He said that these planets could be found if they existed, and it turns out they exist. So that was just like a very brief run through of the history of planets in science and science fiction. So let's move on a bit. Okay, so one of the things David mentioned up front is that I'm the lead scientist at the NASA Exoplanet Archive. So this is how NASA keeps track of all of the exoplanets that we found around the other stars, including the types of stars, the properties of the planets, basically anything we know about them. So one day we're putting in this planet a few years ago, 2018, and I'm looking at it. And if you're an amateur astronomer watching this, then you'll know that all the stars in the sky have multiple names, right? Like every few years, someone else comes along and is like, I have a better way to name all the stars, and gives them another name. So lots of stars, especially bright stars, have many names. So we were putting this system in the archive. It had 3 stars and 1 planet. And I'm putting in all of the names of this star. And you can see there's almost 20. But one of them jumps out, and it's 40 Eridani. And it kind of record scratches in my brain a little bit. And I'm like, what is that? And I wish I could tell you that I immediately knew what it was, but I did. I actually had to Google. I had to be like, why do I know this? Why do I know 40 Eridani? And that's Vulcan. That's the star that Vulcan, Spock's homeworld, is orbiting in the fictional movies and TV show Star Trek. So in real life, this 40 Eridani system has 3 stars. So you see the bright star on the right is A, and then it's orbited by a smaller binary pair on the left. So it's a triple star system. And we found a planet orbiting the A star, which is also the star in the fictional TV series that the planet is orbiting. So that is super cool. And, just goes to show when you use real names of things in fictional properties, eventually you might turn out to be true. So yes, did we find Vulcan? Well, in real life, the planet that's orbiting this star, 40 Eridani A, is not a rocky world in the habitable zone like Vulcan is in Star Trek. It's a very hot gas giant. Actually, it might not be a gas giant. It's a very hot, larger planet than Earth. So not quite. But one thing I'll say is that one of the very cool discoveries from the last 2 decades of planet hunting is that stars usually make more than one planet. And we might have been able to infer that from our solar system. So we have one sun and 8 planets, but we didn't know whether that was always the case. But it seems like if a star makes a planet, it often makes lots of planets. So Vulcan, so 40 Eridani A, we might not have found Vulcan yet, but we found the system that Vulcan would be in if Vulcan existed. So that's pretty cool. One thing I did do was go through the archive and find the most Vulcan-like planet. So a star or a planet orbiting a star most like 40 Eridani A that is most like Vulcan in size, so as rocky as you can get. So this is Kepler 62F. This is an artist rendition of a planet that we found with Kepler that's orbiting a star called Kepler 62. I'm sorry, the names are all terrible. But this is the most Vulcan-like planet we have. That was a lot of fun. So I took it a bit further because I'm a giant nerd. So I went through the Memory Alpha Wikipedia article and looked at every single planet that had ever been name dropped in Star Trek from the start all the way through to Discovery. And there were 938 planets. From those 938 planets, I could reverse engineer that 51 of them were around real stars. And so I had to do a little bit of finagling. Like sometimes there'd be a planet around Taurus Alpha and I'd be like, well, there's no such thing as Taurus Alpha, but there is an Alpha Taurus. So I did a little bit of jiggling and I found 51 real stars. Then I went to the NASA Exoplanet Archive and 7 of those 51 real stars actually host real planets in the real world. So there's at least 7 systems in Star Trek that turned out in real life to have planets. And there's one in particular that I'll spend just another minute on because it's delightful. This is Tau Ceti. So Tau Ceti in real life is a system that has 4 planets. It's the name Tau Ceti, you might realize it's actually a bright star. So here's the constellation Cetus, which is the whale, and there's Tau in the bottom, kind of middle bottom. And so in real life, it has 4 planets. The cool part is in Star Trek, it also has 4 planets. So the Star Trek episodes that talk about Tau Ceti are all taking place on Tau Ceti 4, and the planets are numbered 1, 2, 3, 4. So they even got the number of planets right, which is a lot of fun. So in real life, what is Tau Ceti like? So here's a comparison of Tau Ceti at the top to our solar system at the bottom. And you can see that, so the distances of the planets are to scale, but the sizes of the planets are not to scale. They've been scaled up so we can see them. The shaded green region is what we call the habitable zone. This is where if you had a planet like Earth with an atmosphere, you could have liquid water on the surface. And that's a really important thing for life, we think. So Earth has the solar system has up to 3 planets in the habitable zone, depending on how you count. And Tau Ceti has 2 that are like right on the edge, but they are actually quite a bit bigger than Earth. They're nearly twice as big. And that's where we start to get a bit worried that they're not rocky anymore and they're more like mini Neptunes or mini Uranus planets. So we don't know if these could be habitable. So, it's life, Jim, but not as we know it. If there's life there, it's definitely at the extreme conditions of what we know. So I mentioned Kepler. Kepler 62 was a planet discovered by the Kepler mission. So this was NASA's grand experiment with putting a planet hunting instrument into space, and it went spectacularly well. I was lucky enough to be a staff scientist on Kepler for 4 years and got to participate in finding thousands of planets, which was really very cool. So I'll tell you a little bit about it. It's a 1-meter optical telescope. So this whole spacecraft that you can see here is about the size of a small van in space. And the goal of the Kepler mission, its main goal was to measure how common planets like the Earth are. So when I say a planet like the Earth, I mean a rocky planet in the habitable zone of a star like the sun. So that's 3 criteria that we need: rocky planet, habitable zone, star like the sun. So what did we find? We found lava worlds. So this is Kepler 10. It is a rocky planet the size of Earth, which is great. And it's orbiting a star like the sun, which is great. So that's 2 of the 3. But it has a period of less than a day. So this rock is right next to the star, and the surface is heated up to thousands of degrees. And what happens when you heat something up to thousands of degrees, it's made of rock, the rock melts, and you have this lava world. So is Earth-like? No. But maybe Mustapha-like. We got lava world examples in fiction as well. Okay, So what
It
else
makes
did
me
we
want
find?
to scream out, I hate you. But anyway.
I have the high ground.
Yeah.
Okay, this is Kepler 22b. So it is orbiting a star like the sun, and it is in the habitable zone. So that's 2 of the 3, but it's too big. So again, this is just over twice the size of the Earth. So we don't think it's going to be rocky with a thin atmosphere like the Earth is. We think it's going to have some kind of much deeper, much thicker atmosphere like Uranus and Neptune. And in fact, when we look at planets like this, they seem to have the rough density of water. So it might be that it's something like a water world, which we don't have in our solar system. But we do have in fiction. We do have water worlds in fiction. And in fact, the very first one of these that was found was nicknamed Kevin by its discoverers because it could be a water world. All right. So what else did we find? This is Kepler 186f. So it is a rocky planet in the habitable zone of a star that's not like the sun. So we got 2 of the 3 again. So the star that Kepler 186 is orbiting is an M dwarf or a red dwarf. So it's much smaller and cooler and redder than our sun and puts out quite different radiation. Now, that doesn't mean it's not habitable, but it means we don't know. So a lot of the radiation that comes out of M dwarfs is high energy. So things like X-rays and UV, which are generally bad for life on Earth. There's reasons why you don't like to get X-rays a lot. And there's a reason why we invented sunscreen, because UVs are bad. So this planet might be sterilized by this high energy radiation coming out of the star, or it might be fine. Now, do we have any examples in fiction of a rocky planet in the habitable zone of an M dwarf? We do. So this is where Superman comes from. Superman comes from a rocky planet orbiting an M dwarf. And that's the whole point. When he comes to our planet orbiting our yellow sun, it's got very different radiation, and that gives him powers because it's so different from the light coming from his M star. So like, how cool is it that they included that little bit of astrophysics in the backstory of like one of the most famous comic book characters of all time? Anyway, so this is very Krypton-like. Now, have we found anything that satisfies all 3? I feel like you probably know the answer is no. We would have heard about it. We haven't found any planets that are very Earth-like, like a true Earth twin that satisfies all 3 of those criteria: rocky, in the habitable zone of a star like the sun. And there are technical reasons why that happened, which if you're interested, you can ask about, and we can go into detail in the Q&A. But suffice to say, there's a whole slew of Earth-like planets in science fiction. Naboo, Caprica, Felucia, Beta Z, like all of the franchises have an Earth-like planet because that's the holy grail, right? Like that's what we're aiming for. If we found an Earth-like planet, we know that life has arisen on an Earth-like planet. So how exciting would it be if we could actually find another example? Now, interestingly enough, the fact that we haven't found any yet doesn't mean that we think they're rare. In fact, we think they're common. They're just really hard to find because they're so small and so far away from their stars, relatively speaking. So we actually think that up to half of the stars like the sun have a planet like the Earth. We just haven't found one yet. So we're getting there. We're getting close, but not yet. But we have found just a staggering array of super duper interesting planets that are even unlike anything we were trying to find when we were looking for Earth-like planets. So hopefully I don't get in trouble with copyright for showing this, but this is a classic scene. This is Luke Skywalker on his home world of Tatooine. And what you can see in the background is this classic, now famous binary sunset. Okay, so remember I said most stars are actually in these multiple systems, binaries or triples or higher order multiples. So when George Lucas did this, when he came up with this idea, this visual that Tatooine would be orbiting a binary star, super legit, totally fair. Could have happened. Did happen. This is an example. I think this is Kepler 16, which is the first planet we found orbiting a circumbinary, orbiting 2 stars, a circumbinary planet. And I really like this one because look, he even got the colors right. It's a G star and an M star. It's a yellow star and a red star. He didn't get the sizes right, admittedly, because red stars are smaller than yellow stars. But again, this is in the 70s. This is 20 years before we even found any planets, and 30 or 40 years before we found any orbiting 2 stars. So just like think about the prescience here to come up with this visual and even get the colors right. Super cool. Okay, so This is, someone asked previously about Dune. So Dune was a huge film that came out last year. And before that, obviously, was a huge series of books, very famous. So the world in Dune is called Arrakis. And the whole point of Arrakis is that it's orbiting Canopus, which is a known star in the sky. So, of course, I went and checked in the archive. No planets orbiting Canopus yet. What makes Canopus interesting? It's a red giant. So our sun in 5 billion years is going to become a red giant. It's going to finish burning up its hydrogen and helium in its core. Its core will collapse down into this little ball of carbon and oxygen. But in the meantime, it's going to spend a lot of time just like hanging out, getting big and bloaty and red and being a red giant. And then it's going to puff off all those outer layers into a beautiful planetary nebula for someone else to see billions of years after that. But in the meantime, it'll be a red giant. So we're going to go through this phase. Have we found planets orbiting red giants? Yes. And in fact, even going beyond that, now we have found planets orbiting white dwarfs. So remember I said, what will be left behind is this core of carbon and oxygen in the middle, surrounded by a beautiful planetary nebula. That core is called a white dwarf, and it'll just radiate away heat forever. I mean, that's honestly, our sun is just going to become a very small cooling ball of coal, basically, that just cools forever until the heat death of the universe. Sorry, that's depressing. Anyway, but what we have found is that planets survive the red giant phase. We've found planets orbiting white dwarfs. So that means that this phase that the sun goes through, which is going to last trillions of years as compared to the billions of years it spends as a big glowing spark at the start of the universe, there'll still be planets, which is really exciting because that just increases the amount of time we have for life to evolve by orders of magnitude, by 1,000 times. So that's pretty cool, the fact that we still know that there are planets around white dwarfs. Okay, this is a planet called 55 Cancri E. So 55 Cancri, another bright star, if you can't tell by the name, has a bunch of planets around it. And 55 Cancri E is another one of these lava worlds, like Kepler 10. But actually, it's around such a bright star that we were able to take more precise measurements of 55 Cancri E. And one of the things we were able to see was that it has a very high carbon to oxygen ratio. That means it has more carbon and oxygen than it would have if it was just made out of the same material as its star. So it's overabundant in carbon. So what happens when you take a lot of carbon and you heat it up because you're right next to a star and you crush it because you're in a rock? You make a diamond. So the headlines were very funny when this was first made, like "Move over Tiffany's biggest diamond in the universe found," sort of thing. But this brings to mind, there's a planet in Doctor Who. Again, I'm going to plug as one of the best franchises of all time. There's an episode called Midnight. It takes place on this crystalline planet. It's like a bottle episode. They get trapped in a shuttle and they're, being attacked from the outside. And it's about the stress of the situation and how the different characters handle the stress. It's a very cool episode called Midnight. If you haven't seen it, go watch it. But the point is, it takes place on this crystalline planet with this crazy radiation. So that's what this is. 55 Cancri E is this crystalline planet. Possibly made out of diamond, possibly the largest diamond that we've found, at least. Okay, I think I'm coming up to the end of my fictional planets. So this is, and I'm going to start off by apologizing for the name. This is Ogle 2015 BLG 0051b. And again, I'm sorry. This is a planet that was found by microlensing. So microlensing is basically magic, but it has to do with relativity and the fact that everything with mass bends space-time. So you sitting there right now watching this, you're actually bending space-time just a little bit, but you're actually warping the fabric of space and time, which is amazing. Think about the power you have, warping space and time. So this, what we see is planets that go in front of background stars act like magnifying glasses. They bend space and time around them because they have mass, and they magnify the background star. So what we see is we're just watching the background star because the planet's too small to see. And what we see is that background star suddenly get brighter and then suddenly get fainter again. And you can deduce from the amount of brightness and the length of time it gets bright for, the size and speed of the object that's actually going in front of it. And then you can actually say, oh, it's a planet. And often there's a star there as well. It's very cool. Anyway, so skipping franchises one more time, we're going to go to the Marvel Cinematic Universe. You may have heard of it. So there's a whole arc with the Infinity Stones, and the Soul Stone is on a planet called Vormir, which is described as being at the center of celestial existence. So for us, that would be the middle of the Milky Way galaxy, right? The center of celestial existence. So the thing about microlensing planets is the best way to see them is to look towards the galactic center, because what you want to do is maximize the number of background stars where you could have this coincidental alignment of a planet in the meantime and a star in the background. So all these microlensing surveys are towards the galactic bulge, the center of the galaxy. So this system, Vormir, is 26,000 light years away, this Ogle 2015 BLG 0051b. 26,000 light years away. This is the furthest away planet that we've ever found. So the center of the Milky Way galaxy is about 30,000 light years away. So this is 90% of the way to the center of the galaxy. And it's far and away the furthest planet that we found. So this is as close as I can get to the center of celestial existence, to Vormir, the Soulstone planet. Okay, so that was a rapid fire tour through hopefully one of your favorite franchises. And now I want to talk about just a couple of real planets, because real planets are also pretty cool. One of the things we found that isn't Earth-like, but is super interesting, is planets in resonance systems. So resonances are where the orbital periods of the objects are related to each other with very simple mathematics, like one is 2 times the other, or one is half the other, that kind of very simple integer multiplication and division, very simple fractions. So we do have some examples of this in our solar system. So for instance, the Galilean moons of Jupiter, 3 of them are in a 1 to 2 to 4 resonance. So the inner one goes around 4 times, that's Io. For every 2 times, the next one goes around. And that one goes around twice for every 1 time the one after that goes around. So we see this resonance in the Galilean moons. And we also see that Neptune and Pluto are in a 3 to 2 resonance. So Neptune goes around 3 times for every 2 times Pluto goes around. So we do see these in our solar system, but what we've found around other stars are compact series of planets in very long chains of resonances. So this is a system that I really love called K2-138. And again, it's a garbage name, I'm sorry. It was found by the sequel to the Kepler mission called K2, and it was the 138th planetary system found by K2-138. So it has 6 planets around it, and they were all found by citizen scientists. So that's people at home just looking through the Kepler and K2 data and helping us find planets. So I was lucky enough to be the scientist who was helping with this citizen science project and got to pull this one out of the discoveries and be like, wow, you guys found a really cool system. The cool thing about this system, besides the fact it was found by you guys at home, is that the 5 inner planets are in a chain of 3 to 2 resonances. So again, the inner one goes around 3 times, the next one goes around twice. That one goes around 3 times, the next one goes around twice, all the way out, 3 to 2 resonances. Why that's cool is resonances are music, right? So things being related by integer numbers is intervals in music. It's tones, it's chords, it's frequencies. So this system is singing a song. And the wonderful people at System Sounds actually turned this into a song. I'm going to see if this starts if I click on it. Yes? All right. Now everybody just listen. Okay, there we go. Now what's happening is every time a planet goes in front of the star, it makes a note. And the frequency of the note, the pitch of the note, how high the note is, depends on how fast it's going. So the inner planet is the one making the highest, most constant note. And then it goes out and out and out to the outermost planet, which is making the low note that just happens occasionally. And the reason it sounds pretty, the reason it doesn't sound discordant or out of tune, is because the planets are in resonance. They're all in this 3 to 2 resonance, which means it's musical. So that's your moment of Zen. And I want to invite anybody listening who's interested to go to planethunters.org, which is our citizen science project, current citizen science project to find planets using test data, which I'm just about to talk about. And you too could find your own planet. And then, my favorite part is I get to put the citizen scientists on the papers with me. So you get to be in like a published refereed astrophysics paper in a journal and, work with the scientists and get your planet published. It's super a lot of fun. I really like it. So please, if you have bandwidth and you're interested, go to planethunters.org and start looking through the test data. So I'm going to finish by talking about TESS. So Kepler operated for 4 years as in its original mission, and then 4 years in its follow-on sequel mission called K2. But in 2018, Kepler ran out of fuel. It couldn't run anymore. Luckily, in 2018, NASA launched TESS, the Transiting Exoplanet Survey Satellite. And that's this thing you can see here. So instead of being one big 1 meter telescope, TESS is 4 small 10 centimeter telescopes. That's 4 inches. If you're an amateur astronomer watching this, you probably have a bigger telescope than the telescopes on TESS. These are 4-inch cameras. And the point is, where Kepler did a very narrow, deep survey, so looked at one patch of sky quite deep to faint stars, TESS is doing an all-sky survey, looking over the entire sky at all of the bright stars. And I kind of hinted at this earlier, but with 55 Cancri E, the reason we know more about it is because it's orbiting a bright star, and we can learn a lot more about this system just because we're so much closer to it. We're getting so much more light from it that we can do more with. A lot of the Kepler targets that we found are quite faint, and it's just hard to do a lot more with them, like measure their masses and starting to measure their atmospheres. So the point of TESS is to look at the whole sky and find all of the brightest planets orbiting the brightest stars so that we can study them in a lot of detail with our upcoming missions, like the James Webb Space Telescope, which just launched, and in the future, a big direct imaging flagship that we're planning to launch in like 20 years. We'll be studying these planets. So that's what I have. Exoplanets are cool. Fictional exoplanets are even cooler. Thank you so much, and I'm happy to take questions.
Awesome. Wonderful job there. We really appreciate all this insight into exoplanets, and going through the science fiction ones is just great fun. We have had some great questions in the chat. First of all, someone is watching from Melbourne, Australia. Just thought you might appreciate that.
Hi, Melbourne.
So some folks wanted to know that there was an announcement that I think we're going to talk about later in the show as well, that they're hoping to send a mission to Uranus. And they were mentioning that that mission might help us learn about exoplanets. What do you think we could learn by studying Uranus about all those Neptunes and Uranus and mini Neptunes that are out there? I know they're the most common size exoplanet, but what would we learn?
Yeah, so one of the things that's interesting about Uranus is that it's tipped over, right? So a lot of the planets, when you look at them, they're all rotating and they're all orbiting the sun, but they're almost all roughly in the same plane. So Earth has a bit of a tilt, which is why we have seasons, because sometimes the northern hemisphere is pointing towards the sun and sometimes the southern hemisphere is. But Uranus is like tipped all the way over. It's like rolling around the solar system. And so there's a lot of open questions about planet formation and migration and evolution. So for instance, I said we found these Jupiter-sized planets right next to their stars, which is what Otto had predicted. But we're still trying to work out how that happens. You know, do you have to form it further out and then migrate it in and then stop it before it migrates all the way into the star, right? Like you've got to bring it in a certain way, but not so far. And how do planets interact with each other? So one suggestion is that these hot Jupiters get there because they exchange energy and momentum with another planet and send that other planet out while they go in. So conservation of momentum. And that might end up creating things like Uranus planets. Like, how do you tip something over? Do you have to hit it? Do you have to, change its spin somehow? So going out there and trying to learn more about its structure and its composition, like how differentiated is it? Does it have a core? Does it have a deep ocean? Does it have a deep atmosphere? We just know so little. So getting out there and actually doing that would be so cool. There are definitely things we can learn by looking at Uranus.
Wow. Excellent. Another person wanted to know, have we found any exomoons, and do we expect to?
That is a wonderful question. We have found 2 candidate exomoons. So I didn't really talk much about how Kepler works, but Kepler uses the transit method. So not the wobble method that Otto Struve suggested, and not the microlensing, which I talked about. So the transit method relies on the fact that if you have a planet orbiting your star, sometimes it blocks some of the light. So if you just measure the brightness of the star over and over again with time, if the planet goes in front, you see a little dip in the brightness, just like less than 1% dip, but you see this dip. Now imagine that planet has an even smaller moon around it. And so if the planet and the moon go in front of the star, then the dip might have a little tiny dip next to it, or the dip might be a bit misshapen because it's, instead of one circle, it's like 2 circles that are slightly overlapping. So you can imagine, the difficulty we have in finding things the size of the Earth and then take that down to things the size of the moon and smaller. It's very hard. It's a very, very, very precise measurement we need to make. So far with Kepler, which is the most precise thing that has ever been used to measure light curves, we have 2 examples of transiting planets where we can see some weirdness in the shape of the transit, and it could be because of a moon. So 2 candidates, nothing confirmed yet.
Okay. I know someone on, I think it was on Facebook or someone had asked me, it was Twitter, wanted to know how we can characterize the atmospheres of these exoplanets and how, I'll further it a little bit. How will Webb be able to do that?
Yeah. So there's really two ways we look into planet atmospheres. So the first is using that transit method, which I just described. So if you're a planet with an atmosphere and you go in front of the star, then the starlight, which is getting blocked by the solid part of the planet, some of the starlight goes through the atmosphere of the planet. Now, the molecules and atoms in the atmosphere absorb light at different wavelengths. So, for instance, when we have clouds in the sky, water's absorbing and the light's not getting through, right? Like the clouds stop the light. So whatever's in your atmosphere is going to affect the starlight going through. And interestingly, it's going to absorb starlight at different wavelengths, depending on what the molecules are. So what you do, this is really cool. You look at the transit in a bunch of different wavelengths and you map out how the size of the planet changes with wavelength, because at wavelengths where the atmosphere is absorbing, the planet will look bigger. Because the atmosphere is opaque, it doesn't let the light through. But at wavelengths where the atmosphere is transparent, like none of the molecules are absorbing, the planet looks smaller. So you actually map out the size of the planet as a function of wavelength. And that tells you where are things absorbing and where are they transparent. And then it's like a fingerprint. Certain molecules absorb at certain wavelengths and certain don't. So you can actually just like map that to your knowledge of molecules and say like, this has to be carbon dioxide because it's absorbing here and here. So that's how we actually map out the molecules and atoms in transiting planets. The other way we do is a detection method I haven't talked about yet, which is direct imaging, which is basically what it sounds like. We use a very fancy instrument to like block out the light from the star and look around that for planets that are kind of self-luminous. They're emitting a little bit of light. So again, it's very hard because planets don't emit a lot of light. But if you do find them, and most of the ones we found are much bigger and much hotter than the Earth, so they're radiating out a lot of light, you can actually take that light directly and spread it out and look for molecules and atoms. So that's the two ways. So looking at transiting planets or looking at direct imaging planets.
Okay. One person wanted to know if there's any evidence for planets having been moved outward, kicked out by migrating hot Jupiters. Do we think we've seen anything like that?
So there's a few examples we have. One of them is called free-floating planets. And that's exactly what it sounds like. We have found planets just out there floating between the stars that don't seem like they're gravitationally bound to a star anymore. And one way that can happen is that we can see these free-floating planets is if they get kicked out of a solar system. So for instance, one of the theories about how our solar system formed actually suggests that we started with 5 giant planets. And that, Jupiter, Saturn, Uranus, Neptune survived this like early dynamic part of the solar system, but the 5th one got kicked out. So there could be this like whole population of planets just out among the stars that just got kicked out of their various systems. Now they're all just hanging out like cool kids club, like they're rejects, like, yeah, we're just out here. The other thing we see, so for instance, I was talking about, how do we get hot Jupiters? It seems like stars that have single planets very close in that probably had to have something kick them in, we do seem to see a higher rate of companions around those systems. So either substellar companions like brown dwarfs or small stars. It seems like these systems that have these close-in planets have a companion, and that exchange of momentum and energy with the companion could have been what migrated this thing in. So that companion got pushed out while the planet came in.
Okay, someone wants to know, where are the aliens? So I'm going to change that a little bit and say, where do we expect to find them? Because we can't say where they are for sure, but where would you look?
Yeah, so actually I forgot to say it, but one of the really interesting things that came out of this meeting in Vegas is we've been thinking for a long time about biosignatures, right? So this is, what would you see if you looked at a planet that had life? If you were an alien looking at the Earth, how would you know that the Earth had life? Like if you took the wavelength of the light and broke it out by wavelength, is there any feature that you could point at and be like, that has to be life? So for instance, on Earth, we have the vegetation red edge. So, in as much as the plants around you all look green, if you could see in infrared, plants are actually very infrared. They're very bright in the infrared. We just can't see that because we don't have eyes that see in infrared. But when you look at the spectrum, when you look at the light that comes off the Earth, you see this edge, this like cliff in the infrared because of the vegetation. So That's, for instance, a biosignature. That's a pretty complicated biosignatures. You're talking about chlorophyll and like a very complicated life form that uses that exact energy pathway. So it's very specific. So is there anything simple you can look for that indicates that there might be life? And, you know, oxygen, for instance, on Earth's atmosphere, most of the oxygen that's there now came from billions of years of single-celled microbes and bacteria creating oxygen and slowly changing the bulk properties of our atmosphere to having oxygen in it. But it's not necessarily on its own a biosignature, because there are geological processes that can create oxygen. So one of the cool things that came out of this thing in Vegas was this kind of emerging consensus that maybe a good biosignature is the presence of carbon dioxide and methane at the same time. So there are geological processes that cause carbon dioxide, and there are geological processes that cause methane, but they don't happen at the same time, and they should react with each other in the atmosphere and cancel out's the wrong word, but they shouldn't both survive in the atmosphere. It's a sign of what we call disequilibrium chemistry, that something's out of whack. And one thing that could make something be out of whack is life. The whole point of life is to throw things out of whack, to use energy in different ways and output waste energy in different ways. So this is a cool thing. The reason it's cool is because Webb, the James Webb Space Telescope, should be able to see those molecules. The wavelengths that James Webb looks at, which is in the infrared, cover a lot of the important lines in carbon dioxide and methane. So if this is a legit, robust biosignature, which is still out for debate, but you know, there's emerging consensus, more and more people are like, that could work, then it's something that Webb could measure.
Okay, that's great to hear. Very, very excited about that. A lot of people wanted to know about the aliens. Well, I think we need to wrap up the questions at that point, because we need to move on with the rest of our show, but we could talk exoplanets all night. And we're going to have you back in person.
Yes, I'd love that.
As soon as we're doing shows in person again, maybe we'll do a special exoplanet only night or something like that. Have fun with it. So thank you so much for joining us. It's been a huge pleasure. Absolutely. Yes. And just amazing time here talking exoplanets with you. So folks, I'm going to talk about another opportunity we have that involves exoplanets. It's actually our brand new Samuel Ocean Planetarium show. We have a new show that's opening this month that's called Signs of Life. And I'm going to show you the trailer for it right now. Let's see, back it up one and then move it forward again. I think it'll look like.
Life abounds on Earth. But could it survive? Hidden in the sands of Mars? Inside the misty jets of Enceladus? Within the methane seas of Titan? Or on the thousands of planets we've discovered orbiting other stars? Join us in the search for signs of life.
That's right, Signs of Life. It's opening this month, and if you're a foundation member, which Griffith Observatory Foundation is our nonprofit partner, you can make reservations for the show, and we think that a lot of them are going to sell out, so you might want to join our foundation soon to be able to do that, and pretty exciting. So eventually you'll even be able to buy them online. I believe they're working on that, but that's not quite available yet, but we do have mechanisms to reserve those tickets. So stay tuned, and you'll hear all about the opening soon. So Katie, are you with us? There you are from far, far away. Katie's coming from a remote location this time, so if she starts to fade out on us, we'll jump in for you. But what do you have for us in terms of pretty pictures and space weather? Let's take a look.
This first image are my favorite types of clouds. They're lenticulars over a mountain range, and lenticulars generally form over mountain ranges. And this was taken by Nicholas Gascard. And he also took this next image of a lightning storm, just a gorgeous image from Italy, this one, and on September 9th, 2021. And then on April 17th, SpaceX launched a Falcon 9 rocket from Vandenberg in California. And this spiral you see here was caused by the post-deorbit burn fuel vent of the Falcon 9 upper stage, which deorbited over the Pacific Ocean. So this was captured by the Subaru telescope on Mauna Kea in Hawaii. And a beautiful crescent moon. This was captured by Anthony Perkic. And this is Orion right in the middle of the image. On the left is Canis Major, and on the right is Taurus. This was captured by Todd Kunioka, who's a telescope demonstrator from Griffith Observatory. And this is from Snow Canyon State Park in Utah. Here we have the Como cluster. This was captured by Anthony Perkic, and the Como cluster is a cluster that has over 1,000 identified galaxies. And here are just some of those labeled. So that's an incredible photo from Anthony. And another one from Anthony, this is star Nebula from Leo. And if you were able to wake up early on April 30th, you might have seen the conjunction of planets Jupiter and Venus. That's on the bottom left of this image. In the middle is planet Mars, and on the top right is planet Saturn. And there are labels. See that. This is from Joshua Tree National Park from Anthony Perkic. And then Todd Kunioka, the next day from Joshua Tree, took this on May 1st of the conjunction. And on to some solar system weather. This is the current solar cycle progression. The red line are predicted sunspot values, and the black dots are the monthly values. So we're on our way to solar maximum in 2025, and the sun has been very active this past month. So while sunspots are cooler regions of the sun, the photosphere around them sometimes erupts with outflows of high energy particles called solar prominences. That's on the left, and you can also see the approximate size of Earth to see how big those are. And solar flares, on the other hand, are powerful bursts of radiation, and those, sorry, I think I froze there for a second. So solar flares are powerful bursts of radiation. There's the difference between those there. And Anthony Perkic captured this photo from April 21st of sunspots that have been active this month: 2996, 2995, 2993, and 2994. And sunspot 2993 caused a double solar flare on April 25th, which actually caused a long-lasting radio blackout over Southeast Asia and Australia. And this GIF is of a coronal mass ejection headed toward planet Mercury, and it actually caused Mercury to appear like a comet. So this next image is Mercury's sodium tail taken April 27th. That coronal mass ejection was the 11th. This is by Dr. Sebastian Voltmer. And I believe this was also the astronomy picture of the day, and of course the beautiful Pleiades above planet Mercury. And here's a close-up from Sebastian as well.
Wow.
And just to show you a little bit more of how active our sun was this past month, we had an X-class flare, which is the most powerful class flare, April 17th, April 20th, an M-class on the 22nd, and then an X-class on the 30th, and then another X-class on May 3rd. So the sun is very active right now, and if we're lucky, in some spots of Earth, we can see beautiful aurora from the solar activity. So this one was taken by Göran Strand in Sweden. This is a 360 panoramic view taken in mid-March. And then Göran also captured this one of the Milky Way with northern lights. And Nicholas Hjort took this video to close out Pretty Pictures. This is from April 9th from Abisko.
I like those satellites flying through the image that you see. Heading every which way, it seems.
Yeah.
So beautiful. So more solar activity, maybe some more aurora.
Just fantastic, Katie. Thank you so much for these beautiful pictures and the aurorae, really, really fascinating stuff. Somebody in the chat wanted to know why we don't get hit by more solar flares all the time. Well, the solar flare is the eruption on the surface. Like Katie said, high energy is deposited right there on the surface. It can lift a prominence up off the surface of the sun, and it can cause a coronal mass ejection. And it's that mass traveling from the sun that spreads out into space that does in fact interact with us. It causes the aurora borealis, like you saw there. So we are hit quite a bit by them, but as we head towards solar maximum, they're going to get stronger and stronger. So our magnetic field protects us for the most part, but recently there's been a lot of radio blackouts. If you're somebody that listens to shortwave radio or you like doing that sort of thing, there's been blackouts where the radio signals just don't travel and don't bounce off the ionosphere because the coronal mass ejection interferes. So interesting stuff and great question. So Patrick, let's hear about what's up in the sky this month.
Well, there is a lot going on this month. So starting with this image with a really strange looking moon, and we'll get to that in just a few moments. Looking at our evening sky, if you were to look to the south, just about 10 o'clock at night in the middle of the month, the spring constellations of Leo the Lion with its brightest star Regulus, and Virgo the Maiden and its brightest star Psyche dominate the sky, and much higher up is the reddish orange star Arcturus, the fourth brightest star in the sky. Also on this night, as you look down towards the southeast, you'll see Libra and Scorpius, which are just emerging above the horizon. But between that is supposed to be a full moon, but that moon is just barely visible within this circle, and it's not looking very bright because at that time, the moon enters the Earth's shadow and is totally eclipsed. So May 15th, mark your calendars for that night. There is going to be a total eclipse of the moon. This eclipse is visible in the Americas, so we'll see it here in Los Angeles, also in Europe and in Africa. Well, what happens during a total lunar eclipse? It happens when the full moon moves into the shadow projected into space by the Earth, and there's two components to it. It moves into the umbra, which is the darkest part of the Earth's shadow, where the moon darkens for just an hour or a little bit more. And there's also the lighter part of the shadow, which is called the penumbra. Now, we have a diagram showing the progression of the moon through these two shadows. There you see the umbra and the lighter part of the shadow, the penumbra. And then there's the arrow that shows the path of the moon. So we're going to take you step by step for the phases of this eclipse. First of all, the moon moves through into the penumbra, and that occurs at 6:32. However, from Los Angeles, the moon will be below our horizon and will not rise until 7:41. So we're not going to see this phase of the eclipse. And actually, as it moves into the penumbra, you won't see much until the moon is roughly about 2/3 into the penumbra. So if you're watching this eclipse from the East Coast, around 7:10 p.m. Pacific Daylight Time, you'll see some noticeably darkening on the moon's left edge. And then next, the moon will begin to move and just touch the umbra. And here you will see it will be noticeably darkened on the left edge or the eastern edge. At this time, it will be about 7:28, which is the beginning of the partial eclipse of the moon. And then at moonrise from Los Angeles, when the moon rises, only about a quarter of the moon is partially eclipsed. At 8:29 Pacific Daylight Time, the entire moon is immersed in the umbra. This is the beginning of the total eclipse of the moon. And this will last for 1 hour and 29 minutes. The greatest eclipse is at 9:11. At this point, the moon's northern edge, which is immersed close to the middle of the umbra, will appear a little bit darker than its southern edge. And then you'll see the colors on the moon can vary from deep red to kind of orange, and as it reflects sunlight filtered through the Earth's atmosphere from all the world's sunrises and sunsets. So that is a very spectacular moment. 9:54, the moon's eastern edge begins to exit the umbra, so you'll see it brighten to a a bright yellow or light orange. And this is the end of totality. 10:55, the moon exits the umbra, and this is the end of the partial or umbral eclipse, and the moon brightens significantly. And at 11:51, the moon goes back to full brightness as if nothing happened, and the eclipse is over. Now, we prepared an animation to show you what the eclipse looks like. If you're watching from Los Angeles, from our trails, and you'll see the observatory in the background, and the time span of this is that we'll have the moon at every half hour, just showing what it would look like. So here we go. So we start with moonrise. Well, we invite you to join us for our live broadcast of the total lunar eclipse on the 15th. We'll stream it live directly from our telescope here at Griffith Observatory. Of course, weather permitting. Link to our page is in the red box. So you can always come back to this recording and just go to our webpage, or just go to griffithobservatory.org. Now, with the excitement of the eclipse over, there's also things that are much exciting, just as exciting, which is happening in the morning sky. And in the morning sky, as you've seen in those photographs that Katie showed earlier on, there are 4 bright planets visible. And here they are on the 18th, just about an hour before sunrise. Low to the east is the brilliant planet Venus. Much higher up is Jupiter, followed by Mars. And Saturn is just above the southeastern horizon. Now, technically, there are 5 planets in the morning sky. On the 18th, the planet Neptune is very close to Mars. And this is a great opportunity to see it if you've never seen Neptune before. So let's zoom in. As if you have a pair of binoculars, you can actually see Neptune, the 4th brightest planet in our 4th largest planet in our solar system. It will appear as a bluish star, almost like a star point of light right above Mars. Zooming in further, it's roughly about half a degree just north of Mars. So that is a moment not to be missed. And if you've never seen Neptune, a pair of binoculars will be able to pick it up. Here's an image taken through a larger telescope with 150 power or more. You can see the disk of Neptune, and in this image, just below Neptune is a little faint patch of light, and that is Triton, Neptune's largest moon. On the 24th, the waning crescent moon is to the right of Jupiter and Mars, and if you look the next morning, it's below those 2 planets. And then at the end of the month, or close to the end of the month, on the 29th, there is a close conjunction of Jupiter and Mars. Both planets are separated by a moon's diameter. You can look a day before and a day after, and also on the day of the conjunction, to see the movement of these 2 planets relative to each other. So our moon phases this month. We have a first quarter occurring on the 8th. Full moon is on the 15th. Last quarter is on the 22nd. And new moon is on the 30th. So that's your sky report for this month. So don't forget to not to miss the lunar eclipse. It's going to be quite a treat.
Well, thank you for that, Patrick. In fact, I encourage folks that are in Los Angeles to get outside and watch this eclipse. You don't need to come to Griffith Observatory to see it. We expect to be exceptionally crowded. Traffic will be terrible. If you are planning to come to the observatory, I recommend coming very, very early. Stake out your location. It'll be a fun time, but You can have a great time watching this with your neighbors, your friends, and have a party in your own backyard. You don't need the telescopes at Griffith Observatory to see this. So avoid the traffic and have just as much fun at home by hosting your own eclipse party. This one is perfectly timed to enjoy it with the whole family. So it should be great. Yeah, oh, and also we're streaming this one as well. It was just mentioned in my ear from a little birdie told me to remind you. You can tune in to this YouTube channel right here and watch it all with us and hear what it's like up at Griffith Observatory. Sometimes we're clouded out. You might have a better view at home, and then you'll just hear us complaining that we can't see it, so you never know. Fun times, though. Eclipses are just great fun to watch. Well, now it's time to update you about the excitement that's going on Mars. Perseverance and Ingenuity. Perseverance is the rover, Ingenuity is the little helicopter there, and this is a selfie that was taken by Perseverance, believe it or not. This is from the crater on Mars where it's exploring right now. It's been there a little more than a year. Well, the Mastcam Z, took a very, very interesting series of photos that they stitched together to make a little movie. Let's take a look at it now. Oh my goodness. This is a solar eclipse that's happening here, not a lunar eclipse, but a solar eclipse of sorts. Although that's an awfully strange shape. It's a space potato crawling across the surface of the sun. Those are sunspots in the background that it's crossing right now. You can see some sunspots in the upper right of the sun. But this is a real movie. Believe it or not, this isn't fake. This is what was seen. They stitched together a lot of photographs of it, and it ends there. Now, what was that? Well, that was the moon Phobos. Phobos is a small, rocky moon that orbits very close to the surface of Mars. I forget how large it is. Do either of you remember the physical size of it?
Oh, ballpark of 10 miles.
It's not huge. I could look it up, but anyway, you can Google it yourselves and take a look at it. This is not the first time we've seen an eclipse by one of the two Martian moons. There's Phobos and Deimos, and both were seen by Opportunity. So let's take a look at those. It's a little faster on that one. And then here goes Deimos, which is smaller. It's a much smaller, rocky little moon, and it does take longer to cross the surface of the sun. Now let's take a look at why. Here's a little animation that our very own Chris Butler did for us. And let me get it started here for us. We'll take the sun, and due to the rotation of Mars, the sun appears to go from the east to the west, just like it does here on Earth. And the sun is catching up to Deimos. Now Deimos orbits the other direction. It orbits west to east, but due to the rotation of Mars, it too looks like it's going to the west slightly. Oh, and here comes Phobos. Phobos is so much closer. It moves faster in the sky, travels across the surface of the sun quicker. So Deimos appears to go backwards in the sky due to the rotation of the planet, where Phobos whips around going prograde. So if that confused you, you can watch it over and over again and send us a tweet to ask us how the heck that works, and we'll answer it for you. Another interesting thing that's happened on Mars is the back shell and parachute have been spotted. So remember, Perseverance came in at a high rate of speed. There was heating on that heat shield that slowed it down. They popped open a parachute. They got rid of the heat shield. They ranged the bottom, the ground. They figured their target, and then they finally ejected that back shell. So let me show you here where that happens. Right here, that back shell and parachute get ejected, and then it comes down on a sky crane. Well, that back shell and parachute were spotted from orbit by the Mars Reconnaissance Orbiter and the HiRISE instruments. You can see them there, crashed into the surface. Well, Perseverance has finally traveled close enough that it too saw the back shell and the parachute. You can see them right there. I've pointed them out. The big arrow points them out for you. Now, we got a better view yet. Remember, we have a helicopter on Mars, a little helicopter that can fly around. So they sent Ingenuity to go take a look, and it flew over, or very close to, the parachute and the back shell, and there they are. The parachute on the right hand side looks a little torn up, maybe it's been moving around in the wind a little bit, and that back shell sure enough smacked into the ground hard enough it was broken. Now this was requested by the folks that are building the back shell for future missions. They wanted to know, how did it survive through the heating of the atmosphere as it came in, and also how did it survive the crash? They can estimate the speed that it would have come in on that parachute crashing into the surface and find out how well it did. So people were making jokes about, flying saucer found on Mars, is it sure looks like a flying saucer to me too. But really cool looking pictures. And some folks might want to say, well, we're leaving garbage on Mars. And this is the price you pay in order to go do the science. We don't really have the ability to go pick this up right now, but in the future, these are going to be museum pieces. Somebody's going to go to Mars, pick them up, and put them in the Great Mars Museum for some of the first exploration that we've done there, along with some of the other robot explorers we've sent to Mars. Now, Ingenuity just didn't look at the back shell. It also looked at this interesting rock outcrop. You can see how it looks like it's tilted and it's sticking out of the sand a little bit there, the dust. They wanted to know more about it and learn whether this was tilted similarly to other layers deeper into the crater. Not sure what they found out about that, but it's an interesting picture. Now, Perseverance itself has been hightailing it towards the delta. That's what it was sent to go do, look for signs of life in that delta that was put in by an ancient river into this crater. So here is where it landed, and you can see the path it's taken to drive over towards that delta in that area called Three Forks. In fact, there it is, the delta, and you can see the path that it took. Now, it did explore a little bit the opposite direction. We left that off there to start, and you can see, let me mark it with the laser pointer for you again. It landed and then originally headed off this direction, did some exploring, oh, not that far, did some exploring and sampled the crater floor. They wanted to know what just the crater floor was like, and then they've hightailed it, and in about much, much less time than it took to do that first exploration, it's gotten all the way over here, very, very close to the delta, which is this material in the upper left image there. So they're finally at the main mission target, and they're getting ready to explore there. Now, NASA Perseverance rover hightails it to the Martian delta, and indeed that's what it's done. There's an image of that delta wall. That material was deposited by an ancient rover. Now, there's some interesting material in the foreground there that's sort of lighter in color that might be sort of a mudstone of some sort that was planted in the lake that was there, rather than just brought in by the delta itself. It might have been material sinking down through the lake. Here's a close-up of some of that material, and they were thinking of perhaps using this and analyzing it, doing a sample there and storing that sample to bring back to Earth later. They've declined doing that right now. They don't want to waste too many of their sample containers. They're more interested in that delta material coming from the river than they are in this potential mudstone. So this is what's going on at Perseverance right now, or on Mars right now with Perseverance, and that's a beautiful panorama of that delta material. And the rover is going to head up that direction and start doing more in situ observations with its instruments, but also seek out the right rocks to store and then cache. In other words, put them in a safe location to be retrieved later by a robotic explorer and brought back to Earth, where we can study them in a lab. So let's go a little deeper into space. This is a picture of a giant comet. Now you might say, wait, I don't see any comet in there. But here, right there, we'll circle it. Bernatelli-Bernstein, comet 2014, UN 271. So this was actually originally found in 2014. It's estimated to be a huge comet, perhaps the largest comet we've ever been able to calculate the size of. And here's another beautiful rendering done by our own Chris Butler, showing if you were up close to it what it might look like. But this was estimated to be huge. And in the news, they went a little crazy. They were saying things like massive and hurtling, and the nucleus is gonna run into us, nuclear force, just absolutely craziness. Well, don't believe what you read, especially not on the internet. Yeah. The comet's closest approach is gonna be more than 10.9 astronomical units from the sun. One astronomical unit is 93 million miles. That's the distance between the Earth and the sun. So this comet doesn't come any closer than Saturn. In fact, it goes between Saturn and Uranus's orbit. So it's not hurtling towards Earth. It's approaching the inner solar system. But what is interesting about this is it is already formed a coma and a little bit of a tail, which is unusual for comets that are that far out. So these must be very volatile materials that are being heated up and ejected off of this comet. Some researchers used the Hubble Space Telescope, and they modeled what that coma should look like based upon the smoothness of the background variation, and subtracted it off, leaving the nucleus. And when they measured the size of that, it came out to be a whopping up to 85 miles across. Now, it might be a little smaller because they didn't get this exactly right, but that is huge. That's ridiculously big. You know, Hale-Bopp was 46 miles, and everybody thought that one was ginormous. Halley's only 7 miles across, and that one's a super well-known one. Another well-known comet was Churyumov-Gerasimenko, which was visited by the Rosetta spacecraft, and it was only about 2.5 miles across. There you can see it compared to Los Angeles. So let's compare this new comet to Los Angeles. That's right, it would span between Malibu, that's the circle on the left, all the way out to San Bernardino on the right-hand side, so Riverside to Malibu. And I don't particularly like that rendering, but that's how it goes. Wow, that one went forward on its own on me. I don't know if that was animated in, but what the heck. You can see here another rendering by Chris Butler of what it might look like up close to this comet. So pretty cool stuff. I can't wait to see as it gets closer and closer to us. We'll learn more and more about it. It'll outgas more. We'll get more spectrographs on it, and we'll learn what what it's made of. Probably made of comet-like stuff, but the details, I'm curious if it's different than other smaller comets. This one being, a much, much larger object. And now, about a month ago, astronomers discovered a galaxy as it was a long time ago, and it's far, far away. Yeah, okay, I know, cheesy, but it was just May the 4th, so I had to do that. Oh, let me pull this forward a little bit because my dog wants to get by. Okay, there he is. He always has to interrupt the show. What this is the most distant galaxy that we have found to date, and it's that red little smudge. Yeah, it doesn't much look like a galaxy to you, but we believe this is probably a star-forming galaxy or a quasar at the center of a galaxy. And here are the other ones that used to be the most distant galaxy. They also are little red smudges. Now, why are they little red smudges? Well, the redshift, as objects get further and further away from us, the expansion of the universe actually stretches that light out. So it makes it redder and redder and redder. So in order to find these, you look for this sort of red dropout in the wavelength. You'll have light, then all of a sudden the light goes away because, well, they can't produce too many X-rays, too many gamma rays, too many UV radiation with these stars. So it's redshifted so far that it literally drops out and you end up losing those. So anyway, this is the sort of data we use to find them. And this new galaxy was identified at a redshift of 13.3, which puts it just hundreds of millions of years after the beginning of the universe. It's almost, it's between 13.4 and 13.5 billion years ago. And the universe started about 13.8 billion years ago. So this thing is really, really far apart, just crazy. So anyway, they're going to find more and more of these. The Webb telescope, JWST, will be particularly good at finding these, and we'll push it closer and closer to those cosmic dark ages and the first stars. So that's one of the reasons we're excited about the new telescope, which, by the way, all 4 instruments are now in focus. So all of them are working like they expected. They're all in focus, and I can't wait for them to finish the checking out phase and start getting those observations within the next few months. Patrick, I know we're sending a mission out to another unusual object. What can you tell us about it?
Yeah, the anticipation is over after years of hearing about this mission. This is the Psyche mission. So the Psyche spacecraft, as you see in this artist's conception, this is NASA's mission to send a spacecraft to study the metallic world called 16 Psyche. And it's a very exciting mission. And just a few days ago, the spacecraft was all boxed up and carried on a C-17 to Kennedy Space Center, and it will be removed and prepared for launch. Here is an image of the spacecraft, actually at JPL in Southern California, being wheeled down the corridor, the completed spacecraft, into a large vacuum chamber where they simulate the environment of space and also the launch vibrations and heating and stresses on the spacecraft. It passed with flying colors. The spacecraft has very large solar panels. Here's one of them, which is 37 foot long. And the reason it needs these solar panels is that it powers an ion drive, and it also needs to operate where Psyche is. And it's located between the orbits of Mars and Jupiter in the middle of the asteroid belt, where sunlight, it needs as much sunlight as it can to power this the spacecraft. Now, what do we know about Psyche? Well, we have these images, radar images that show the shape of the asteroid, which is about 140 miles across. We also have these images taken by the Very Large Telescope, giving you a hint of some of the coloration or the shading on this asteroid, and also from the shape. People have modeled these from these observations, the shape and some of the rough topography of the asteroid. And this is an interesting thing. This is a 3D print from Arizona State University of Psyche, and the model kind of matches the artist's rendition. So those craters are kind of really, I mean, they're just artist impressions of where we think the craters are. But the shape is very much what it would look like. This 3D print took about 86 hours and 43 minutes to print. So they're going to paint it later to approximate the light, what it would look like as far as the coloration of the asteroid, and that's based on spectral emissions from the asteroid. Now, what makes this a special asteroid? Well, 1% of the asteroids in the asteroid belt are actually metal asteroids. And how do they form? Well, here's a five-stage process where at the beginning of the solar system, material gathers through gravitation, and you get an early planetesimal, and that planetesimal could be fairly large, such that metals such as nickel and iron will sink to the center of the planetoid, and in a process called differentiation. And then also there's radioactive minerals and materials that will cause volcanism, it causes heating as well. And then eventually the planetoid cools down and it has a solid metal center, iron and nickel and other very heavy metals. And then just above it is a large covering of maybe about a mixture of metal and rock, and then you have the outer crust, which is the dark part of it. Somewhere during the history of this particular asteroid, there were impacts. There were lots of asteroids that impacted and could have worn down the crust and part of the rocky metal mixture above it, leaving the exposed core of what was a planetoid in the asteroid belt. Now, we have clues of what that might look like from meteorites that we have. On the left, here is our very own iron meteorite here at Griffith Observatory. It's 269 pounds. And that would be representative of the core of where it came from a asteroid, core of an asteroid. And then just on the right, there is a what we call a stony type iron meteorites, which is a mixture of iron and rock, which represents the material above it. Now, we won't know exactly what this asteroid looks like up close until Psyche spacecraft arrives at Psyche in 2026. So it will go into orbit around this asteroid, and for 21 months, it will study the asteroid starting from an orbit of 457 miles to a mere 53 miles at the end of its mission. So very exciting, and we're looking forward to that. Now, going from metal to water and water ice, the Europa Clipper, we have some news from that as well. This is a mission to the icy moon of Jupiter. And this icy moon has an icy crust, and possibly beneath that is an ocean of liquid water. So a very good candidate for possible studies of life, if there's any life there. And work has begun on that. And here we see some of the components there, just going clockwise from the left. You see part of the propulsion system. Next is the ultraviolet spectrometer. And then on the right there is the high gain antennae. Most of the flight hardware is scheduled to be completed by the end of this year, among some of the other 9 instruments that will be arriving at the assembly point at JPL later on in the year. So that's kind of very exciting. The timeline on this mission is launch is in 2024, arrival at Jupiter and is in the year 2030, and this spacecraft will spend a year going around Jupiter, altering its orbit, so it will intercept Europa, and there will be 45 flybys in a span of 3 years. So it will give us a lot of information about this moon that we have not had before. And incidentally, in September of this year, there will be a very close flyby of Juno around Europa, and that will give us some of our first pictures just ahead of this Europa Clipper mission.
Well, fantastic. That's going to be a very exciting mission once it finally launches. And speaking of launches, Chris, let's hear about this month's launches in your Out to Launch section.
Yeah, a quick roundup of what's going on in the world of space launches. First of all, from last month, you might remember, we had the launch of the first private mission to the space station, meaning no government astronauts. There was one experienced space flyer before, but he's now an employee of a private company, Axiom. Axiom is a company that wants to establish essentially space stations of their own that would be both for research and for tourism. And this is kind of a test of that. On April 8th, this group of 4 went up to the International Space Station aiming at 10 days on board, but they got an extended stay courtesy of bad weather in the splashdown zone. They ended up getting 17 days up there. They're back on terra firma now. I hope they've enjoyed their stay. Of course, they can't leave a little mint on your pillow at the end of the night because it would float off the pillow. But otherwise, I think they had a great time at the hotel. Talking about launches here, the Axiom 1 launch was occurring in the same month. In fact, only about 3 weeks before the next launch from the same launch pad, the same company launching the same type of spacecraft. This is the SpaceX Dragon. The NASA crew rotation mission, Crew 4, launched a very short time later. If you look at the dates there, April 27th, Crew 4 launched. This is a launch cadence from the same launch pad of piloted space missions with astronauts we haven't seen since 1965 in the Gemini program. So really impressive. We're really picking it up. The Crew 4 has arrived on the space station. You see them there meeting some of the Crew 3 and also some of the cosmonauts that were on board. Crew 3 didn't hang around for a long time. That's a lot of people to feed up there. So Crew 3 has come back to Earth. In fact, last night they splashed down off of Florida and they are safely home. As far as other things going on, the Artemis moon rocket, we talked a lot about that. A lot of excitement for its first test with no astronauts flying to the moon. And I told you there was a chance we might have a flight in maybe June, something like that. Well, that's not going to happen. They did roll the giant vehicle out to the launch pad at Cape Canaveral. They performed tests. There were some small problems with it. The launch pad equipment itself had some problems. There were some small hydrogen leaks. That's going to need to get fixed. And also there was one valve that was misbehaving on the second stage of the SLS Space Launch System rocket. That'll need to be fixed too. They had been planning to take it back to the hangar. That was always in the plan, but the repairs will take a little longer than expected and should be maybe August. We could look for a launch to the moon. So that's fine. The other giant rocket, SpaceX's gigantic Starship rocket, even larger than the Space Launch System, they've been waiting for the Federal Aviation Administration to complete reviews of environmental impact and things like this for launching from South Texas, where SpaceX has their test facility. That has not been granted yet. Although there are reports they're getting close to finished with it. I should say we don't know if, when the report is done, it will be an approval or a rejection. We will see. But SpaceX has been busily setting up a launch pad at Cape Canaveral in Florida, where we know those launches would be okay. So again, maybe in the summerish months, we may see a launch of this giant rocket. Hope so. We had an interesting thing attempted here. SpaceX is famous for reusing its rockets, saves a lot of money. Other companies are beginning to experiment with that too. Rocket Lab, that launches out of primarily New Zealand, they have a smaller rocket called the Electron. It doesn't have enough fuel to do a powered landing after launching satellites. It's out of fuel. But they have an innovative system where they've decided to basically fall back to Earth. Just let the rocket come back down in a controlled way, then deploy a parachute. And the idea was to try to catch that parachute and bring the rocket to land it on a ship, dry, without ever having touched salt water, which is bad for electronics. Well, they gave it a try, and they were able to catch a rocket that had been launched to space. Came back, they caught it. They ended up having to release it a few seconds later, though, because the behavior of the Electron rocket underneath the helicopter, they weren't entirely comfortable with it. They'll get that figured out on the next test. This was just a first test, and it went well. This is something other companies are looking at as well. The United Launch Alliance is getting on board with the reusability too. They've got an idea a few years down the road of maybe recovering the engine section only of their brand new Vulcan rocket. So look for all kinds of exciting things coming in the future on rocket reuse. The Capstone mission, that's a small 55-pound satellite, a microsat, that they're going to launch. By the way, Rocket Lab again, the little Electron rocket's going to launch this to orbit the moon. This is a test flight to check out a complicated orbit that's never been flown before. NASA wants to see about maybe putting a space station with astronauts around the moon using that orbit. This will test it out. Launch has just been delayed to the next launch window. That starts May 27th. So sometime after that, we may see the launch of this interesting little mission to the moon. The Chinese are getting ready to send up a robotic resupply mission to their space station. There should be in June, there will be taikonauts, a group of 3, going up to the station. Right now, there's no one on the station, but the Chinese will be doing a lot more with their taikonauts going up there, and even some new modules on their station later in the year. And here's something blast from the past. The Boeing Starliner spacecraft. This one, you may remember a while back, years ago now, they tried to fly it and it couldn't get to the space station because it had computer glitches. And then more recently, they put it out on launch pad. We're trying to get ready to do a redo. And there were valve problems. So they had to send it back to the shop and then back to the company to get work on it. Well, they're going to give it another try here. So we have got May 19th as the redo on Starliner. This is very important for Boeing. This really needs to work. And talking about anticipation, we've talked a lot about Psyche, and I'm really excited about that launch coming up August 1st. That's when you need to be watching for this. As you can see in the picture there on your left, the spacecraft has arrived at the Cape. They are assembling the rocket and putting it together. This is the big Falcon rocket. All 3 cores of a Falcon Heavy rocket, the most powerful rocket on Earth right now, aiming to send this spacecraft to Psyche. Launch will be August 1st. And that's it for the world of launches.
Well, that's pretty darn exciting. And I can't wait to see that Falcon Heavy go. It's amazing to watch those 3 cores come back and land. I'm curious, are they going to land any of them out on drones, drone ships, or are they all coming back to land? Do we know?
Well, the attempt will be made to recover the side boosters probably on land, but the core booster, the center booster, has so much energy at the end of its burn, they can't get that back to land. So that would be on a drone ship for sure, and then hopefully the other 2 on land. That's what I understand the plan to be.
That makes complete sense. Thank you. Well, another exciting month of launches.
Oh yeah.
Now, time to move on to our section. Daniel, are you out there somewhere? There he is. Daniel, welcome. Daniel is going to tell is one of our employees at Griffith Observatory. He's a museum guide that often can be found in the halls explaining the science and what goes on. And currently he's off in school, but he comes to our meetings and brought up an interesting story about another decadal survey. This isn't the astrophysics one where we talked about new space telescopes. This was a planetary science one. So Daniel, what was in this planetary science decadal?
I'll definitely go ahead and talk your ear off about it. I'm personally really excited about this decadal survey. I'm studying planetary science. So on April 19th, when they released the decadal survey for the years 2023 to 2032 to the public, I was very excited. For those of you who don't know what a decadal survey is, it's essentially a publication that outlines the highest scientific priorities and missions pertaining to, or specifically to this one, planetary science and astrobiology for the next decade. Think of it like a to-do list for planetary science and astrobiology research for space agencies. The National Academy of Sciences made a lot of recommendations for the next decade. But tonight, we're just going to go over some of the top priorities listed in the survey. The highest priority listed in the decadal survey was to send an orbiter and probe mission to Uranus. Yes, you could. This decade, you can make all the jokes you want. It's really important that we're going to visit Uranus because we haven't visited Uranus via spacecraft at all since Voyager 2's flyby in 1986. So it's extremely, extremely important, top of the list, top of the line, that we send a mission to study Uranus's interior, its atmosphere, its magnetosphere, and its ring system like never before, including a lot of the moons in that system that haven't been imaged in great detail at all prior to this. So it's very exciting. I know there was a big buzz on the chat tonight regarding visiting Uranus. The next priority mission listed on the decadal survey is to send a orbiter / lander mission, or cleverly called Orbilander mission, to Saturn's moon Enceladus. I am extremely excited for this mission. Enceladus has always piqued my interest. And what this mission would do would be to analyze fresh plume material, both from orbit and on a 2-year landed mission. The mission would gather geochemical and geophysical data for future experiments, while also directly searching for evidence of life. So I'm extremely excited. I'm excited that Enceladus is finally getting its due. The third highest priority listed in the decadal survey is a continuation of NASA's exploration program on Mars. According to the survey, the Mars sample return mission should be completed pretty much as soon as possible without a change to its current scope. So we don't want to do anything extra. We just want to make sure we can get all the samples that Perseverance is collecting, and we send it back up over to Earth. The next priority would be, of course, in that exploration program, would be the Mars Life Explorer, which would seek out current and historical records of life on Mars, should they exist, and assess its current habitability. Assess the habitability on Mars. Interestingly enough, for the first time ever, the decadal survey actually recommended planetary defense missions to be developed. The highest planetary defense mission listed on the decadal survey is NEO Surveyor, which would be a space-based infrared telescope tasked to survey near Earth objects, otherwise known as NEOs or NEOs, so to speak. After that, the next priority listed for planetary defense would be a flyby recon probe designed to assess a specifically targeted NEO that remains to be determined, and possibly even impact the NEO to assess different ways to redirect such NEOs. The last part of the decadal survey that we're going to cover tonight is regarding spacecraft categorization, and more specifically, the funding allocated for each category of spacecraft. NASA categorizes much of their current spacecraft within these four categories: flagship, new frontiers, discovery, and explorer. You can see where some of your favorite spacecraft fall along this funding tier system. As of right now, there are budget limits that define each of these categories. Science teams have to keep their financials in mind when proposing missions for funding, because this is essentially which program they're going to be applying for funding to. Well, good news. The Decadal Survey is actually recommending increases to the upper limits of both the New Frontiers and the Discovery tiers of funding. Imagine the science. Imagine the science that could be accomplished with these budgetary increases. More money equals more science. Sorry, Explorer. Sorry that you're out of the loop there. So it's really exciting that we get these recommendations from the Decadal Survey. The 2023 to 2032 Decadal Survey is going to have a lot of weight for the space agencies, federal government, and research institutes in regards to how they approach science recommendations. For reference, as you can see here, the 2013 to 2022 Decadal Survey, known as Visions and Voyages, made recommendations that led to the development of missions like Perseverance, Ingenuity, and Europa Clipper. So as someone who's studying planetary science, it's such an exciting time to study planetary science. I'm super excited, and Twitter was ablaze with so many planetary scientists celebrating and reveling in their excitement for this Decadal Survey. With that said, as quickly as their social media pages blew up, they kind of faded back away to their science hidey holes, just as Alex Parker here did on Twitter, said, until the next decade. So yeah.
The question I have is, do they make the same noises as the cicadas do? And
I hope not.
If I do, I will make sure to let you know.
Yeah, we'll find out for sure. Anyway, Daniel, fascinating stuff. I can't wait to see some of these missions. I really want to fast forward on the sample return mission from Perseverance. As soon as it gets these samples, I want to know, was there once life on Mars or not? So now, one place that we know there's, well, I won't say there's not life inside of it, because Pluto's turned out to be a pretty weird place, and it could have an ocean down under there for all we know. There are some folks that think it might, but a really weird result came out recently that they think there are actually ice volcanoes on Pluto. And you're seeing here sort of a side view of one, and they give off sort of a slushy material. If I fast forward here, you can see the different compounds. I won't name them all, but there's nitrogen and sort of the CH materials and things like that. But there are differences around it that make them think there were flows, that there were actually, well, lava flows of a slushy water-like material that was mixed with nitrogen and methane and other ices. So we go forward again, you can see, again, sort of that view of what might be, get my laser pointer out here, what might actually be sort of the core of a volcano, and then these materials that they've marked in different colors, and these hummocky terrains that don't have a lot of craters on them. So they wonder, how do you get a terrain that doesn't have very many craters? Well, it means it's new. And if that terrain is new, it's been resurfaced. So maybe it was resurfaced by an ice volcano. So again, you can see this sort of hummocky, hillocky, little hills all over the place material that's very unusual, but it's seen on Pluto, and it may be evidence that there are actually these ice volcanoes. And then lastly, if you do have ice volcanoes, it might explain why Pluto's atmosphere has these layers and is actually a little denser than a lot of theories would have predicted. Well, I shouldn't say theories, but a lot of hypotheses predicted that Pluto's atmosphere wouldn't be quite as dense as it is, especially this late. It's moving away from the sun. Well, if you're replenishing some of that material through volcanic action, you could actually make it thicker. So, well, that's our last story for tonight, folks. So thank you again so much for joining us. We'd like to thank Dr. Jessie Christensen again for being a wonderful, wonderful guest talking about exoplanets. I know everybody really enjoyed asking questions and all her terrific answers. Go back and rewatch the show again, or watch it when we edit it down to get even more out of it. I'm sure there's going to be things we all missed. Patrick, so thank you so much for the Sky Report and everything you do to make All Space Considered great every month. Chris Butler, folks were saying in the chat they really enjoyed your your animations and the drawings you did, well, the illustrations really of these comets and things, that it's highly appreciated. And also, of course, Out to Launch is terrific as always. And I want to thank our fans out there on the YouTube chat, our fans that are watching the show. We appreciate you all tuning in month after month to watch it. And also, once again, Griffith Observatory is owned and operated by the City of Los Angeles and the Department of Recreation and Parks. And we like to thank Griffith Observatory Foundation, our nonprofit partner, for so much that they do for us. They help us keep our Samuel Ocean Planetarium shows current, help fund things like the equipment we need to bring you this show remotely. They help us update our facilities. So they're really important for what we do, and we appreciate folks that have made donations tonight during the show. Now we're going to end tonight by re-showing the beautiful opening sequence we did, which was actually made of animations that Chris Butler and even our own Patrick So made. He made one of these animations as well. They're from our module that we bring to our school kids. And we're going to play the music that was put together by Bill Gruneberg, only this time we're bringing you the vocal edition. So that's right, you're going to hear his vocals and hear all about exoplanets. But once again, thank you for joining us, and we hope you enjoyed the show.
Thank you.
I looked around the galaxy to see what I could see. I said I looked around the Milky Way and this is what I could see. Thousands of exoplanets pretty as can be. There were big hot Jupiters and Earth-like terrestrials and even one smaller than Mercury. I saw some big hot Jupiters and Earth-like terrestrials and even one smaller than Mercury. Can't wait to look at them all through JWST. Yeah, take it away.